Welcome, Precalculus students, to week 7 of distance learning. This week, we are going to be looking at the second calculus idea, which is derivatives. With that being said, let's jump into derivatives. A derivative of a function is one that will tell you the instantaneous slope at each point. Another way to think about this is derivatives allow you to go from a position function, where is it at each location, to then a velocity function, telling you the instantaneous velocity at a particular point. And then a derivative of the velocity would tell you the acceleration at a particular point. Now what we're going to do today is look at a very simplistic view of derivatives. If and when you take calculus, you will have at least 2 to 3 units dealing with specifically derivatives. So, of course, you're going to be jumping in much deeper into these ideas when you go into those classes. So we're just going to be looking at just the surface level of derivatives. The idea of a derivative and how it's linked into this unit and into calculus is that it is from the idea of a limit. As the limit of h going to 0 of f of x plus h minus f of x over h, that is a way that you will calculate a derivative. Now, since we're going to be looking at this very simplistic view, we're going to be utilizing the algebraic ideas of utilizing power rules, product rule, and quotient rule. These will allow us to do our derivatives algebraically. For the power rule of a derivative, what ends up happening is any function x, say x squared, okay, x of n. What's going to happen is the power rule allows you to take that in and pull it out in front and then subtract 1 from that power. So if you look at x to the third, the derivative would be 3x squared. So the power goes out in front, and then you subtract 1 from that power for your derivative. Now, a pretty neat thing about this is it allows you to find your min-max values of functions by taking that derivative and setting it equal to 0 and solving. When you guys were taking Algebra 1 or Algebra 2, a lot of times when you dealt with quadratics and you had to find min-max values of the quadratic, whether it was the min or the max, a lot of times you use the formula negative b over 2a. If that rings a bell with any of you, that was actually derived from using derivatives. So with that being said, this idea of getting the min-max from setting the derivative equal to 0, that is what is called in the calculus terms a critical point. Now, when looking at a product rule, your derivative, or in this case, how they write it as d over dx, derivative in terms of x, if you have a multiplication going on, the way to derive that would be to take the derivative of the first function times the original second function plus the original first function times the derivative of the second function. Lastly, the quotient rule. If you're looking for the derivative in terms of x of two functions being divided, that would be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom function squared. Now we're going to go ahead and look at some examples dealing with each piece from this lesson and its notes. Now let's look at some examples. Example 1, find the derivative and evaluate at the given values. So part A, f of x equals 6x squared plus 7, and then we're going to evaluate at x equals 2 and x equals negative 1. So for part A, it's just a power rule. So we take the 2 and multiply it out in front. So 2 times 6 is 12, x to the 2 minus 1, or 1. And then the constant of 7 goes away. So this 7 is gone, and our derivative is just f prime of x, or the derivative, equals 12x. Then from here we plug in our two values. So in this case, 2 plugged in would give us 24, and then negative 1 plugged in would give us negative 12. And that's the answer for part A. So part B, f of x equals negative 5x squared plus 2x minus 12. So each one of these we're going to be doing the power rule for. So negative 5x squared becomes negative 10x. The 2x becomes 2. And then the minus 12 goes away. So the 2 came out in front of the negative 5, so 2 times negative 5 is negative 10. And then 2 minus 1 will be the power, so 1. And then for this one, the power is understood to be 1, so it goes out in front, so 2 times 1 is 2. And then the power goes down 1, so there is no more x there. And then the negative 12 goes away. So the derivative for this is going to be negative 10x plus 2. Then you plug in your two numbers. 1 plugged in, negative 10 times 1 is negative 10 plus 2 is negative 8. And then 4 plugged in is negative 40 plus 2, which is negative 38. So I hope that you guys are seeing through the first two pieces in example 1 here that all you're doing with just the functions that's given to you is you're taking the exponent of the x value and multiplying it by the coefficient out in front. Then you're going to subtract 1 from that exponent. If the exponent was 1, then the x would go away. If there wasn't an x or a variable with that number, then that number goes away. Example 2, find the derivative. Again, we're going to be utilizing the derivative here, but these are a little bit different in the way that they are set up. So part A says f of x of the square root of x to the third. So in this case, when you're given radicals like this, I like to use our 8th exponent rule from Algebra 1 and Algebra 2, where when you're given a radical, you can turn it into a fraction exponent. Where the fraction exponent is power over root, so 3 over 2. So another way of writing this is x to the 3 over 2 power. Then you can go ahead and use your power rule by taking 3 over 2, multiplying it out in front, and then subtracting 1 from that exponent. So the derivative in this case is 3 over 2, x to the 1/2 power. So part B, f of x equals 1 over x to the fifth. We still want to look at it with exponent rules in mind. So instead of dealing with it on the bottom of a fraction bar, why don't we move it to the top by making our exponent negative? So 1 over x to the fifth can be rewritten as x to the negative fifth. Now we can go through the same process of deriving. So negative 5 going out in front and subtracting 1 from the negative 5. So the answer is the derivative equals negative 5 x to the negative sixth power. And then lastly, part C. Part C, we have a fraction here. f of x equals 4x to the fourth minus 3x squared plus 5x over x. Now this allows us to see how some cases may be set up for the quotient rule or division here, but we can actually make them into a simpler power rule. In this case, there's an x on the bottom. Every piece on top has an x. So what we can do is cancel out an x from each piece and the x on the bottom. So for this case, 4x to the third minus 3x plus 5. Then we can go in and derive using our power rule. The 3 comes out with the 4 to make 12x to the second power minus 3. And that is our answer, 12x squared minus 3. Example 3. The height of a bungee jump is h of t equals 20t squared minus 160t plus 330. And this is from 0 to 6 seconds. So that's what t is. 0 to 6 seconds is how far this function is measuring. What we're going to do is find the minimum and maximum heights of this jump. We're only utilizing the 0 to 6 seconds. Since we're looking for the min and max, we're going to take our derivative and set it equal to 0 and solve. Our derivative of our height function is 40t minus 160. So we're going to take that and set it equal to 0 and solve for t. So if you take 160, add it to the other side, and then divide by 40, you'll get t to be 4. So that means that we're looking for the minimum and maximum heights between the times of 0, 4, and 6. There will be a maximum, a minimum between those 3 choices for time. So we take our 0, 4, and 6 and plug it into the original height function, because that will tell us the height of the person making the jump at 0 seconds, 4 seconds, and 6 seconds. So if you plug 0 into the original function, you'll get 330. If you plug 4 into the original function and calculate, you'll get 10. And if you plug 6 into the original function and calculate, you'll get 90. So that means that we have a maximum of 330 feet in the air and then a minimum of 10 feet in the air. So that person's bungee jump went from 330 feet to 10 feet. Sounds a little scary. Okay, so the max The max is at 0 seconds, we're at 330 feet, and the min is 4 seconds, we're at 10 feet off the ground. And that's example 3. Example 4, we're going to be dealing with our quotients and product rules for this one. So we're going to find the derivative of each of these 4 functions listed. With these last 4, we're going to need a little bit more room, so I'm going to go ahead and erase everything above it so we have some room to write out each one in a lot bigger format. Part A. What I like to do in these cases, since we're going to be utilizing derivatives and pieces like that, is I'll start up here and I'm going to write it out just like the formula is. The derivative of the function is the derivative of the first piece, which is 5x to the 4th plus 26x times the second piece, 7x to the 3rd minus 5x squared plus 18 plus the first original function, x to the 5th plus 13x squared times the derivative of the second. 21x squared minus 10x. And then from there, we're going to distribute, FOIL, and combine our like terms. So just for that first distribution, this is what you're getting. And this is what it is simplified. Then you're going to do the second by foiling. So So x to the 5th times 21x squared is 21x to the 7th. Negative 10x times x to the 5th is negative 10x to the 6th. Plus 273x to the 4th. And then the last one is minus 130x to the 3rd. That finishes up the last piece, and so now what we're going to do is combine our like terms and finish up the problem. And that's your answer for part A. I know this is a long process. It's very tedious in terms of going through, making sure you get your derivative. And then it's mainly a lot of foiling and distributions. That's what you're going to notice through B, C, and D. A lot of foiling, a lot of distributions when we're doing these. Part B. So for part B, x squared plus x to the third plus x times 8x squared plus 3. Derivative of the first times the second, so 2x plus 3x squared plus 1 times 8x squared plus 3 plus, and then the derivative of the second times the first, x squared plus x to the third plus x times 16x. So just doing the first, we get 16x to the third plus 24x4 plus 6x plus 9x squared plus 3. Sorry, messed that up. And if you combine your like terms, you'll get 24x to the fourth plus 16x3 plus 17x squared plus 6x plus 3. And then we will add in our second distribution here. So you're going to get plus 16x3 plus 16x4 plus 16x squared. And then combine your like terms to finish the problem. So our answer is 40x to the fourth plus 32x to the third plus 33x squared plus 6x plus 3. Now we're going to be switching to the quotient rule for the last two. So let's go ahead and look at the next one. So for this one, it is the derivative of the top times the bottom. So 7 times 12x plus 5 minus the derivative of the bottom, or 12 times 7x minus 10. And that's going to be over the bottom, 12x plus 5 squared. So all we're going to do for these quotient rule problems is we're going to be distributing on the top and then simplifying the top. So the top goes to 84x plus 35 minus 84x plus 120. So when you combine like terms, you get 155 over the denominator of 12x plus 5 squared. That's your quotient rule. So now we're going to look at part D, the final example dealing with the quotient rule. There again, to do the derivative, it's the derivative of the top times the bottom, so 6 times 2x squared plus 4 minus derivative of the bottom, or 4x times 6x, over the bottom, 2x squared plus 4 squared. Then we'll distribute and simplify the top. 12x squared plus 24 minus 24x squared over 2x squared plus 4 squared, and then combine your like terms. Negative 12x squared plus 24 over 2x squared plus 4 squared. And that is your answer. And that finishes up the last example for this lesson. So now what you're going to see is the assignment posted below. As always, please feel free to reply, post, chat, email questions. I'll be glad to answer them. And I'll be praying over each and every one of you guys this week. And I hope to see you guys really soon.